G'day everyone, this is Salmak Yingli, your Quantum Odyssey tour guide. Happy Thanksgiving Eve. This is going to be your Thanksgiving holiday season, and it can also be said as the unofficial start to the winter season. It's the last American holiday before the winter vacation, which means Hanukkah, Christmas, New Year's Day, or Kwanzaa. And to celebrate the 2026, which is going to be the year of FIFA World Cup soccer, as well as the Winter Olympics. So this is our live stream again for Ring 3. I am very sorry I have failed on Ring 3 twice in a row. So this time I'm going to get the live stream for you once more for your Thanksgiving holiday. I also apologize for not having these live streams during the other Thanksgiving, the Remembrance Day, no Halloween, so because I have been very busy with some circumstances. The diagram there is a 4-adder, and I have color-coded this 4-adder to highlight that it consists of an OR of 2 half-adders. Namely that the half-adder part A and B would be input, the XOR part would represent the intermediate sum, and the AND part will represent the carryover part, which is one of the 2 ways to activate the carryover out. The C, which means carryover in, would also be activated if the C itself is on, or that if S is on and C is on. So there is the other term for the C out occurs when C is on and S of M, so intermediate M, is on. And this also happens that if one of A and B is on but C is not on. The blue portions represents the first half-adder, namely those with the inputs A and B and without the previous carry over, which let's call this the C in playing. The sum would be denoted as S of M, so sum intermediate, while the carryover would then be one of the ways to activate the carryover out. So in this case, AB would be on, while C would be off. Below is the diagram of a 4-adder. I have color-coded the 4-adder to highlight that it can be made with 2 half-adders and an OR gate. The blue wires represent those from the first half-adder, that is, from the 2 inputs alone. The 2 inputs sum would then be processed as an intermediate value, let's call this sum of M, S of M, while the carryover of these 2 will be denoted C of M. The previous carryover C of in, let's just call this C, would be highlighted in orange. So here is our diagram. The second half adder would use C and S. So we have the A and B half adder, and then we also have the C and S half adder. So in this case, the final sum would evaluate to high when the sum of int m evaluates to high, XOR if the C evaluates to high. So in this case, S would be on if there is 1 or 3 of the A, B, and C's being on, but not 2. Otherwise, we would end up with this thing being on, but this thing will be off, or vice versa. This thing will be on, yet these two will be off. For the carryovers carry over, so we have that will be on if we have the combinations either of A and B and then C. So exactly if 2 of them are on. So if all 3 are on, S will be on, C would also be on, because we have A, B, this thing is on as well, and C, however, will be off, but nevertheless the AB itself is able to activate the C. Otherwise, we would have AC or BC would able to activate the C out using the bottom path, which means AC or BC exclusively. So let's start our live stream once more. I apologize for having to re-live stream this twice. Here it is. Here's the run. So here are the most recent updates. The introductory tutorial has been updated to 3 sections. However, there is a new challenge that we will address. There's a new challenge we will address. So here is the rerun of our ring number 3. And please remember that, interestingly enough, I may have to dub the original number 3, and namely the civic one, that will be redubbed. So this is strictly a re-recording. This is the half adders. The half adder, we have the X gates, can be made using X gates and a Toffoli and a C naught. Here in this case, we have the bit 0, bit 1 to be serve as the row of A and B. However, B can also become S and then C. So this is what we have. I have also moved my portrait to the bottom right, so it won't cover the instructions. Sorry for that. So we have this. Without looking at the boards, here's what we have. A, B, and S, C. A becomes 1, but S is 0 and C is 1. So what does that say? It says that A and B themselves have to be 1. Here's another example, except this time the qubit rows has changed. From there, we have this. We now have A to be qubit 1, B to be BS to be qubit 2, and C to be qubit 3. So we put it on second qubit, first qubit, ground qubit. So notice, how can you tell this in the circuit level? The one with both C's is A. The one with the C on one of them and an X on the other is B and S. The last one, the one with only an X, is the C, the carryover. Here is the custom gate. In this case, we have this represents the A, this represents the B, S, and third one represents the C. A, B. Okay, so this doesn't work. So here we have C to be 0, B, S to be 1, but A to be 1 as well. So that means the B is 0. Notice that the row of B converts into the row of S. Transistor logic and digital circuits, full adder. This time we have the inputs A, B, and C, namely the C in, and two outputs sum and count. So it can be constructed with only 4 qubits, except this time the count remains as count. It's reset to 0, so count. This is the A, this is the B, B to some intermediate, S of M, and this is the C. The C is not touched once the B became some intermediate. Then the C would serve as the B in the second half adder, which then this B would become the overall sum. Here we have, in this case, we have the third qubit to be the count. We have A to be 1. We have B to be 1. We also have sum to be 1 as well. So how would you approach that? But there is no carry. Notice that an uncomputation step is there specifically to convert the sum intermediate back into B. In this case, the C would then take double row as S. Here we do it in the opposite order. A, B, S intermediate, then S, then B back into B, then we have the C and S. So we have this. A is 1, B is 1. The sum is also 1, and the carry is 1. So that means all three of them are on. Here is an example, this time with a custom gate. From this, we have this A, B, C, and S, then count. Here we have the B is on, but however the sum is off. And the carry is on. So what does that say? you will keep the B, and then you will have the other one has to be a C. So that means the carry is there. Okay. There has been a few rating changes. The qubit destruction used to be immediate, but now it's a beginner. 2-qubit warm up. These are the 2-qubit ones. We will focus on the 3-qubit gates for the red path, which I have failed once, but I have passed the other time. This one is easy, so we have this. A yellow and a yellow together is another way to form a red. This one is going to be an entanglement problem, so we have to add a there. Okay, now we will have to perform an H. Okay, now we have like a shortcut. On the right side, we can apply another X, and then another Z. So we can do this in only 6 gates. Actually, the best one has 5. This is a very easy entanglement problem. So an H, and then internally we also have another H. So H, then X. Now we apply simultaneously Y, and then we can also apply a Z over there, and then a ZX. Here is a brilliant solution, but it's not optimal. It doesn't matter if it's optimal or not. Turn them imaginary. Okay, so you're only allowed these polys, the S and the H. We can use an H again over there. We could try an error. That. Okay. There, it's just like a Y gate might also be used to switch a rule. Now it's turned them imaginary, but you won't like this color combination. You want the negative of that. So how would you do that? Okay, so here we can switch with another Y as well. An X. Okay. There we can also use another X and an X. Two X's, this would then flip the colors. Now it would flip the colors, and then let's flip the signs as well. Now the colors are flipped. I got a brilliant solution, but again, like, This one is a very easy problem, so all you have to do is perform a double X on the ground and the first qubit. So there are 11 of them. Okay, now we have to reverse everything. So we can flip the right half as well. So right half, that's the most obvious choice. So right half, we perform an cross. Okay, now there's an entanglement. We use Y over there. That would create a yin-yang, so it doesn't really work. Okay, now it works. We apply an H, then we apply a Y once more. Notice that the distribution of solutions for the red ones are considerably more irregular. This one is a classic yin-yang and then a Bell state problem. So we first create a yin-yang, HSH. So this is the classic way to create two yin-yangs. However, we notice that the right one is off by a quarter turn, so that's Z and A and S would have to be applied. And it's applied on the middle qubit as well. Now we apply an H. We can do this in parallel. So we do an H, and notice on the right half, so C, and then X or Y, CY, CY. This one is easy to optimize. Okay, this is when like crap gets hard. The reason why is you have to convert half of them, keep half of them as yin-yangs, and keep the other half as intact. And you have to do this simultaneously. So this is going to be a considerable challenge for us, especially like both are flipped. Can you do this without wasting and resetting? So here, let's do the first attempt. We HSH back. HSH doesn't work in this case because there are eigenvalues in that case. We try to do that again, so we use SHSH. Okay. SHSH. But this would waste 4, so doesn't look too good. We SH, we can just do the SH. And then we can then attempt to, there's a slight rounding error, we can then, on the right half, we can use, we can create a yin-yang over there. We add a Y on the first to ensure like there is no mismatch. Okay, now this left half seems to be fixed. We can use extra S's to correct the colors. Correct the S to correct the colors. We use the X again. We can then correct the colors once more. So we use another X. Okay, now the left side is almost done. The left side is almost done. We have to repair this right node. So this is when we do another Y gate. So X won't work in this case. However, we can do an S to S, and there we have solved that half. This red can easily be changed back into yellow. So in this case, we have 5 to go. We need to correct these colors, and we need to flip them back. So we flip. Let's correct more. Let's see if these colors can be corrected. Okay, so we correct the colors. Let's correct it this way. So this needs to be corrected as well. So let's correct the colors. Now we can see if the green can turn it back into a yellow. So we can use yellow, then we can then use a Y over there. But okay, now one of those, okay. I think I forgot to add, okay, this thing needs to be moved. This has to be moved to the right. Then we have to ensure like this has to be corrected as well. So we have to correct we only have, okay, here we can then okay, we now apply let's see if the color combination is correct. So we need this. Okay. Okay, so now both sides are corrected, and we can now focus on the right half side and flip them back with only one layer to spare. So this is when problems in the does not matter. And notice that how unusually distributed this is. Now, given like this, we have to fix it back. I believe there is a shortcut for that. Let's see if such a shortcut exists. But that will create eyes and this won't work. Oh, there are eyes. There are eyes and there are the yin-yangs, so there is a hidden shortcut in this type of problem. But the way it's distributed is wrong. So yin-yang, two yin-yangs, and then the I. Okay, so here we need to, it's now just an H, the H would work. So we now flip the sign. Now the colors match. The colors match, so there's only, let's say, the solution involves just 2 gates. But many of them attempted to solve with as much as 29 gates. I don't suppose you've noticed I've quietly replicated the quantum state as a new input. So they're actually trying to tease you with that. And you are given with this same difficult combination over there, but because there's something mirrored, let's say if we can like take out the eyes. Okay, after the H, we take out the eyes. But now we have to watch out for the rounding errors. So this one will trip a lot of people because you have to reduce from something hard to something easy, but then it turns out it's not easy at all, it's hard. Because there is (59) and 51. Okay, so here we are able to solve for the 51. However, there's a 0.5 and a 0.01. So how can you even do that? So 0.49. 0.49. Let's do that. 0.49 and 0.51. Let's try adding these two together to see if the yin-yang works. This will create a 0.7 and a 0.01, so I don't think this is suitable. Let's try this. Try again with 49 and against the 49. Let's try H again. This is where the 69 is created. We now have a 51. So 69s can be created by combining the two 49s. We have the 51s as there. 51 is solved. We now try to move the 49, but the 5 and 0.01 is bothersome. It's a very cleverly hidden eye. So it's bad news. So you will get stuck on this one. You will get stuck, but there are a few hints. The 51 has to be intact, the 69 is intact, so how can you create the eye? The eye is ideally the one that is created after there is some discrepancy after handling the this. So X So we have a 49. The 49 will be merged to a 69. We now SHS once again. So a lot of controls. Okay, so we have a 51 and a 49. We add them together. So a 49 and a 49 mismatched to create a 69. So that means there's a 51 and then there is a slightly off 51. Let's try this again to see how the eye can be created. Okay, so let's skip like a number. The last one, however, is the easy one. It's believed to be easier. So 69 and 49 and 51. Okay, the first hint is you want to, on the right hand side, you want to move to the very right. Then we apply Toph H. The 0.01 is there. We now have a slight mismatch over there on the 69 and the 71. So we attempt to merge that again. Okay, now we have a 99 and then the 0.01. We move the 99, then we can finalize the merge. The neg should turn into let's combine the neg, and then we perform another merge. Now the 0.02 is there, the 0.99 is there. So we apply an H over there. So we now are missing a S dagger. So how to do that? S dagger, you have to do it with 2 gates. So the last problem is should be significantly easier, but again, the solutions distribution is highly irregular. Let's say it's really even. Like there's as much people who have barely working solutions and those which have very efficient solutions. And I did not make the most efficient one. We will work with 3 of 10, which is the one that grinds a lot of gears. 0.49. Let's try a slightly simpler method. We do an X, double X, then we entangle. Maybe there will be a shortcut there with a Toph. We then apply an H to reduce this to, we'll create a 69. Over there. So we have a 69. Here we have a very close eye, and then there is a yin-yang. So yin-yang over there. We then try an SHS on the yin-yangs to see if they split evenly. So they do not split evenly, so the way to do that would change. Now I'm able to find the shortcut. 0.5 this is considered finished, so however we have a 0.5, but it's looking for neg 0.51. So there must be something, there must be a slight issue. You cannot like the I in another order. So to resolve a small imbalance, the bigger one should carry the thing, not the smaller. So but we know that 0.69 is correct. Let's try again. Okay, now we should have solved that after repeating SH on the right half. Now our final goal is to move them to the correct spots. Here we know that the large is on the right hand side, so we first do this. And the 0.51 is the one that should be moved to the left. So 0.51 would then be moved with an X. We then X 2 halves. Okay. We do the entangling, so now we put the 69 to the right. So CX. So now the one we have left is to deal with this thing, with the last one, and but we do have like a considerable amount of leeway. If you check the number of depth, it allows like 25. So 0.01 and then I 0.5. We need to somehow focus on the right half of each pair, now the space. So we flip over there to the right as well, so flip to the right. Now the one with both would be have to move to the very right. So if both are on, we can apply a Y over there. Now we apply another X on the middle. Now we apply the necessary S gates to solve the puzzle. The signs match, so this is our solution. Done step by step after discussing a shortcut. And it is a brilliant solution, and I am with 36 gates, the best has 22. Some has like all 60 gates. And I did score in bracket 6, so it's decent. Again, it's only for demonstration, but if you are able to get a very good solution there, 22 or even better, then round of applause. Ideally, we could use that to breach every gate, given the combinations, but brute force maybe. The solutions are subject to change. This is the other 3-qubit problem. So now we have cracked the 3-qubit vault. They trust the 3-qubit system as if they were free of imperfections. So we'll show them otherwise by showing small unassuming rounding errors. Once inflated, trigger chain reaction that never anticipated. Each overlooked discrepancy becomes another step towards a sudden unstoppable collapse. So the theme of this Missing Sage Red puzzle, Red series, is to exploit floating point errors. So no more warm-ups. Okay, so this is nothing more than an SX and AH problem. So SX, let's try a triple SX. So this is a demonstration of triple SX. Okay, this is a very easy entanglement problem, so you just do H, Y. As well, except this time we can also apply another Y and another Y, so that's all. So so we can do a Z, 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 S, Z, S. We can also try to shorten the process using Y's as well. So Y, Y, Y. Okay, now we have something more beautiful. So Y, Z, and then Z. But it's still not the most efficient. So I didn't win this prize. This is another very easy entanglement problem. So we have two yin-yangs. We split the yin-yang again to each half. And then we apply X, and we apply CX. This is an easy problem again, so we use an H, SH again, because we're not given the Y gate. Then we perform another X, and then another X. So interesting enough, the second of the 3-qubit red puzzles are the easier of the two. Here we are not allowed to use a T gate, but we need to convert this into yin-yang space. So how to do that? We're also not allowed to use a swap as well, so we don't want to make it difficult for you. So the first solution is use HSH to convert this back into I's, to yin-yangs. Then we have to match the yin-yang colors as well, so it looks like HSHS H to create two I's, two yin-yangs, and then we also have to add more Y's to match the color as well. Okay. Now, on the right half, we split this into two. So we split this into two. And then now it's nothing more than applying X, and then a S, S, Z that. So this is another easy controlled gate problem. So cracking the vault is, interesting enough, the easier of the two. So about that, my application stopped loading. So let's try this again. Okay, now this should be like another easy one to tackle, but here's a problem. We have this 42 and the 0.7, so there is an unequal superposition. There's an unequal superposition, which I like to call them hidden eyes. You don't want hidden eyes or another obstacle when trying to crack the vault. So 0.5 and 0.35. So now we'll create a positive-negative combo to create okay, this does not work quite right. We can combine a 5 against 0.25. Then we combine to form 0.53 and 18. So it does not work. So this is the one that's tricky. Okay, here's the hint. The 35s is solved. So we use an X and we only work in the right half. We want to combine a 35 against 25. Thoughtfully in both ways, and then we see like the positive negative cancel out to force 25 and 35 we mix together. Let's say like if the negative positive combo would create a hidden eye. So 43, that's a hidden eye. 43 and 0.7 are opposites. We now combine the 43 and then 0.7 with Toffoli S, okay, Toffoli Z. Okay, it's going to be a CZ gate. So now we are nearly done. We run with CX. Okay, now it looks like a swap is required. You do not want a swap. You don't want a swap. So there is where I have to got this thing screwed. So okay, so we do the swap. And then we use all of our layers for this part. Okay, now this is where the trap came into play. It says 42, not 43. This is when this problem tricked you. So that means the splitting the 0.5 will not work. It will not work. Because it splits into 0.42. How can you do that? Let's try splitting the 35. Work directly from the right hand side. So we use the 35. We deal with the 5 later. 35, we split the 35 into 25s. Okay, now we have a 49. This is where the trick comes into play. 49 would split into 2 of the 25s. We then do the merge. 35 and then a 25. Then we, on the right hand side, we now apply another one. Okay. This looks mergeable, so we merge this back into a 25, 42, 3. Okay. It looks like a swap might be required in this case. So we'll have to put the 7, which is the partner to the 42. Then we finally apply an X to solve the problem. So this is the trick. I have the 19 gate, the best has 14. Good, now go ahead and round this back to the ground state. I've made sure it's packed with enough rounding errors to keep you entertained. Enjoy the moons while they last. They might just be our final dance with the three-qubit system. I bet moon is the original term for the yin-yangs. So 0.7 and 0.7. It doesn't look very unitary. It's unitary, but barely off. So slightly off. 42 and the 7s are partners in crime, so we apply an A. over there. We then work with the left side, Toffoli H. Now Toffoli H again, Toffoli CX. Okay, and now add an X again because it can be done in parallel, and finally we have our solution. In fact, this one is optimized. So 4-qubit, this is going to be a hard. We will conclude our session with "You are ready." Your mind is ready, your intuition is perfect, your eyes see clear paths through quantum logic. This is your first impossible puzzle, and you're presented with 3, 4, 5, 6. 6 layers and several intervening CXs and Toffolis and a T-gate. You are given 25 layers, but some of them are occupied. So you have effectively like 18 around. It starts with the 0 state and you have to get it to the 15 state. So the tip is you want to ensure that after each barrier, the qubit combination, only one sigil passes through to simplify everything. This is easy. So basically converts into, there's many secret gates and T gates. This is easy. This, you can just combine this with X on the second, and then we can also apply an, see if this is gonna mess you up. This might mess you up, but so we can leave the rest empty. What you don't want this time is, we can actually add a control gate to take out some of the things, but we want to ensure that at this level we want things to be simple. Let's see if we can make this simplified, even simpler. Let's go with a yin-yang anyways. So yin-yang. We now have 4 yin-yangs over there. Let's see, we can take out one of them, but this won't work very well, so we don't need to take out. Now on the right hand side we can just use an SX to simplify, and then after the second layer we have a single yellow sigil. So this is easy. We can try to use now we have use the C gate to negate one part of the mystery gate. So now only a single red sigil passes. Now this is when the things get tricky. You don't want to put it over there. You don't. It creates eyes. So this, layer is a particularly nasty one. So what? What? Yes. Secret what? There is a hint. This is not in the initial early stage release, but so we have to test out which ones work and which ones do not. This one does not work. Okay. Interestingly enough, I found a shortcut. So now the whole third layer is taken out. Now it creates rainbows. Let's see if there's any that looks good. Okay, here's another problem. This looks like an uneven RX gate. H can be done before to negate the effects over there, and then we have the RT. This is where RT comes into play. We RT across the third qubit. Now we have something very simple. Now we RT and then we can do the H. Okay. Oh, I did like one gate too early, but now we can see the 71. Then we have the I. The I goes all the way to the very first, and then we should get like a 1, hopefully. Okay, so there's another work that has to be in the form of a RX gate. So let's see. Okay, this part actually has a bit of an H involved. So let's simplify by making the colors the same. Let's try splitting this, and then we'll have a merge. Let's see if this is possible. Okay, here's another hint. We can try to like negate the splitting layer to simplify. Now, with a uneven split, which is this thing gone, we can now process our final piece. The SX can be turned back into an, but we only have like 3 layers left. So we can use an H. We can use an H. Let's SX, an H, another H, an SX, and then we can finally finish this with a T. So And here we did. We solved our impossible puzzle. The best I saw is have 11 gates. So you are ready. We have, but interesting enough, I only got bracket 1. Almost every one has bracket 1 in this case. Let's do the mechanics of a fracture once again to see the updated one. Let's see how fast I can go. So so close. Maybe time matters, but so again, these mechanics of a fracture problems, these are all like these super simple drills for you to get acquainted with these gates hands-on without reading the instruction sheet. Time capsule, humans and computation. This will conclude our live stream. So Seeker, if computation is new to you, open this module first. Here you will meet the very first ideas humans use in computation. Bits, 0 and 1, and the bit strings that comes from them. So 00, 01, 10, and 11. You will discover why humans build all information on top of these simple symbols, and how these forge reveals the logic that powers both classical transistors and quantum systems. This is a casual narrated lesson for the absolute beginner. So I mean absolute beginner, a message carried across time from humans to you. This is Paula Marie's session.
Hello, I will be your guide throughout this interactive journey, designed to show you the true beauty of computation, up to its most modern form, quantum computation. When you're ready to start, press the Next button. The earliest known tool for computation is the Sumerian abacus, and it was thought to have been invented in Babylon around 2,500 years BC. Its original style of usage was by lines drawn in sand with pebbles. As Sumerian villages morphed into great city-states, the first information overload in human history occurred. The invention of the abacus allowed the Sumerians to compute the at the time vast information which needed solutioning to sustain civilization. Perhaps counterintuitive, as Sumerian villages morphed into great city-states,
Okay, this one is not narrated.
While the Sumerian abacus, perhaps
Okay, that's a
how we
glitch.
might see it, our systems for processing information have in fact simplified since then. Base 2, while the Sumerian abacuses were computing in base 60 with complicated rules, our electromechanical programmable computers of today use just base 2, also known as binary. Because modern computers use electric current and do many binary calculations in parallel, there is no need for larger bases. Base 2 uses only 0 and 1. Think of it as the on and off states of a switch. These switches can be engineered in many ways, but most modern computers use a type of electronic switch known as a transistor. The implementation of base 2 calculations is called a bit. The visual map you see is a representation of the mathematical workings of a computational bit. The falling ball represents the bit's current state throughout a computation. Now it starts at 0 and exits at 0. Each time the ball reaches the bottom, computational time moves forward. If we want our bit to start at 0 and output at 1, we need to give it an instruction. Press the Tab key to open the list of available instructions. Our first instruction is now available to be added in order to change the output of the bit. It is known as an X gate because of its behavior. It will swap the values of our binary system.
Okay.
If the input is 0, the process of computation using this instruction will output a 1, and the reverse would happen if the input is 1.
Okay, the X gate, let's call this an X gate because it looks like an X.
By adding our first instruction to the circuit configuration, we have created the most basic computation algorithm possible. Drag the X gate to the circuit configuration. Good. Now let us look at a computation using 2 bits. The visual map on the right represents the process of computation on 2 bits combined, following a naming convention called bit strings. A bit string is an immutable, contiguous sequence of bits. A 2-bit computation is defined as arriving from a bit string input to a desired bit string output. All possible bit string inputs and outputs are shown in the visual map, ranging from all bits in the bit string being 0, 0, up to all being 1, 1. In this case, our input is defined by the location where the ball starts, the 0, 0 bit string state. Our desired output is marked at the 0, 1 bit string state with a static ball. Remember that a bit string is the immutable combination of both left and right bits. To do a computation that changes the bit string 0, 0 to bit string 0, 1 requires that you add an instruction just on the rightmost bit. Add a single X gate on the rightmost bit in the circuit configuration. Notice how after adding the X gate on the right bit, our visual map showed the behavior for all possible bit string combinations that the ball could have travelled through, depending on the input it started at. Now our computation has an input bit string 0, 0, and we want to output 1, 0. map look different with the X on the left bit in order to accurately reflect all the possible swaps of all binary strings, regardless from where the ball starts. This is particularly helpful to build your intuition. Now we want both bits to swap from input 0, 0 to output 1, 1, as is shown by the mark. Add the gates accordingly. What if we want to do a complex instruction? Let us connect our left and right bits in such a way that if the left bit is switched to 1, only then should our right bit switch to 1. Place the missing gate so that our arrangement of transistors outputs 1, 1 in the current configuration. How about the other way around? Only if the right bit is switched to 1, then should the left bit switch to 1. Place the missing gate accordingly. Very good. This set of instructions, if a bit is 1, only then make the other 1, 1, is known as a controlled X-gate operation, XOR. It requires the placement of 2 gates, a control on the bit that we want to read, and an X on the bit that we want to swap after the first one becomes 1. Place the gates to achieve 1, 1 again.
Okay, it's not an X or it's a CX.
The visual map accurately represents the series of instructions that we are giving to our bits, as our computation, the ball, evolves according to your instructions from an input state to an output state. Solve this puzzle by bringing the ball to the marked output state. In the field of computation, these blocks you are now using are called XOR and NAND.
Okay.
Marked the start of a new way of thinking about computation. It was Erwin Schrödinger who devised a well-known thought experiment, known as Schrödinger's cat, which highlighted this dissonance between how we understand computation and how nature does computation. In nature, very counterintuitively to human intuition, atoms have properties that can be in 2 states at the same time. The thought experiment is simplistic. We place a cat in a box with poison in it, and we can't know with certainty if the cat is either alive or dead at any point in time until we open the box. As much as it defies human intuition, matter can, at the atomic level, be in 2 states at once. Much consideration has been given to whether this law of nature could be used for our own computational needs. In 2020, our modern transistors are now so small that the laws of nature can interfere with our computation and prevent us from building smaller transistors. If we want to be able to compute more information, and much faster, we need to redesign the way we think about computation altogether. Fortunately, with the amazing technology we now have, this is possible. This new way of reasoning is called quantum computation, and at its foundation is the principle of harnessing the natural behavior of quantum particles in order to do computation. It was Richard Feynman in 1981 who showed that certain important problems for humanity to better understand the universe, such as the behavior of atomic particles, will never be efficiently modelled using the computational logic we have built thus far. The solution is to build a quantum computer capable to compute by using nature's own computational rules. To experience computation at its frontier, we will now replace the notion of our left and right bits with qubits. The X and controlled X gates remain just as useful, yet to fully exploit quantum computing, we will now start computing using the law of nature that allows for two states at once, known as superposition. Although we are now back to a single binary, a single computation can now become two by using the H gate as an instruction on a qubit. Place the H gate in the circuit configuration. In the case of two qubits, the visual map accurately represents. In the case of two qubits, observe how the H gate splits a computation with input 0, 0 towards 0, 0 and 0, 1 if placed on the right qubit. The left qubit remains at 0 for both balls, representing the computation. Remember that the visual map at all times shows all possible inputs and outputs at any point throughout the computation, including the effects of the H gate. Place the H gate accordingly. The effect on the left qubit is the same. Our computation becomes 0, 0 and 1, 0, with the right qubit remaining unaffected. Achieve the computation states shown on the visual map. What do you think will happen if we place both qubits in superposition? We could obtain 4 possible outputs at the same time. As beautiful as this may be to observe, scientists are still working on finding an explanation for this eerie phenomenon of quantum particles. Some even argue that all these outcomes exist in many worlds at the same time. Place the H gates to achieve the desired outcome. Our qubits defy our intuition further. If we send an instruction to our qubits that splits our computation state into 4 possible outcomes, we could cancel some of these states and amplify the others by using the H gate again. This is another phenomenon observed in nature, known as quantum interference. Place a further H gate to achieve the desired outcome. Whenever we have multiple states, if we introduce another H gate after the first set, we observe quantum interference. By placing a third H gate the right qubit, we see quantum interference in action, annihilating all bit string states where the right qubit could be 1. We could go as far as to annihilate all the possible states where any qubit could be 1, by placing H gates, returning everything to 0, 0. You might now be thinking, how can this lead to larger and faster ways of doing computation? There is no better way to build understanding of this than to start by looking at Einstein's famous spooky action at a distance thought experiment, known also as the EPR paradox. Albert Einstein was not happy with quantum physics. He argued that there is a certain computation that could be done using the laws of nature that makes absolutely no sense. Hence, quantum physics should be, at best, incomplete. Without access to a quantum computer, he used mathematics to show if we measure the left qubit to be 0, the right qubit would always be 0. If we measure the left qubit to be 1, it appears that the right qubit will be 1. Makes sense, right? As we discussed, controlled X will swap a bit if the other bit is 1, however strange it might be that the H gate forces the other bit to be both 0 and 1. But what if we take qubits extremely far apart? How can we, by observing the state of one, immediately know the state of the other? All experimental evidence to date suggests that nature does work following this mathematical framework. We plan to make use of this physical phenomenon, that we call entanglement, to teleport quantum states, subject to certain limitations that we will discuss in a further tutorial. Solve the puzzle by placing the two gates, Control and X, in the same computation order. Build the quantum algorithm to resolve the EPR paradox again, to achieve the marked output state in the visual map, both 0, 0 and 1, 1 at the same time. Remember, the X gate flip states, Control X in the same computation row, will enforce the entanglement rule, as in classical computing, that if, and only if, the qubit having control placed on it is 1, then, and only then, flip the other qubit. Lastly, to achieve superposition and use quantum interference, make use of H-gates. This will allow you to calculate using just 2 qubits, creating up to 4 different computations all at the same time. Before I go, I will leave you with this. The power of quantum computation grows exponentially with the number of qubits, useful in order to efficiently simulate systems of similar growth, such as traffic optimization, financial modeling, better artificial intelligence, materials and drug discoveries, climate change, and many other applications still waiting to be discovered. To simulate such systems on a quantum machine, we need to consider 2 things. First, find a way to encode the real-world problem on the bit strings shown at the input of the circuit, to then discover an efficient quantum algorithm in order to obtain the desired output. This quantum visualizer is designed for doing proof-of-concept algorithms and to build a visual, rather than a mathematical, intuition over how quantum physics is used to compute. This tool is compatible with all universal quantum computers that we have today. I hope that you have enjoyed this tutorial. You have just learnt all the phenomena behind how to do the most advanced form of computation, quantum computing. Starting with this series of puzzles and going onwards, you are
Analog
able to
computing,
construct quantum algorithms
deep learning.
with your newfound logic. If you wish to test the skills that you have just learnt, you can now do the series of puzzles provided that work through the concepts you have just been introduced to. Good luck.
So this is going to be the conclusion of our re-recording of the 3rd live stream. We will do our next layer on that Thanksgiving Day, the very American Thanksgiving Day, near the end of fall. Peace out, everyone.